Hello and welcome to a new session for this online course on Introduction to Embedded System Design. I am your instructor Dhananjay Gadre. In this session, we are going to consider a very important aspect, which is to be able to create analog waveforms using digital control. There are many methods of generating analog voltages with the help of a microcontroller, and one such method uses the timer building block, that is a common peripheral in many microcontrollers, and MSP430 is very rich in this resource. We have already introduced ourselves to the use of timer, how we can generate interrupts at predetermined intervals and periods using the timer. In this lecture, we are going to look at various methods of generating pulse width modulation signal, which is one method of generating analog voltages, using a software approach as well as using a hardware approach which uses the timer. So, the main topic of our discussion today is to be able to generate analog voltages. We will take two approaches, a software method which does not require any timer, but will tie down the CPU in just generating that analog voltage. It will not be able to do many other things simultaneously. If we want to do that, then we must rely upon the timer operation, and many timer operations offer a PWM generation mechanism, and we are going to explore that in this lecture today. So, let us begin. Pulse width modulation, as the name suggests, is a mechanism of modifying the width, of modulating the width of a pulse waveform. Here, by modifying the width, we are able to change the average value of the signal. Here is a sample signal. We see there is a certain on time, as you see here, the time for which the signal is high. Of the total time period of the signal, the ratio of the on time and the total time is defined as the duty cycle, say D, multiplied by the voltage, the maximum voltage of that pulse waveform will give you the average voltage. So, V average by changing the duty cycle of this waveform, which can go from 0 to 1, I can vary the average voltage from 0 to VCC. This is a very good method of generating analog voltages. Now, the voltage itself appears rectangular. How do I get out of this the analog voltage which is proportional to the duty cycle? Well, you can do that by applying this signal to a appropriate low pass filter. We will see how to calculate the value of that filter and what sort of filter is used. The property of pulse width modulation signal is that as you increase the on time, the duty cycle of the pulse width increases, and so does the average value. Now, if we applied a PWM signal to output device such as an LED, and if we can keep the frequency of the PWM signal, FPWM is equal to 1 by here the T on plus T off, T on plus T off. If the frequency of the PWM signal is much higher than the rate at which the human eye can perceive on and off of a LED, then the eye will not perceive the LED as on and off. Instead, it will be able to only perceive a intensity which lies between 0 and maximum, proportional to the duty cycle. And this is because of the limitation of the human eye called persistence of vision. Apart from LEDs, you can use a pulse width modulation signal to drive a DC motor, and by changing the duty cycle you can change the average voltage applied to the DC motor, and thereby you will be able to control the speed of the DC motor. We have discussed this in the past. The speed of a DC motor is proportional to the voltage applied across the terminals, and therefore, this is a good method by which we can mimic an analog voltage from a digital signal. Here are examples of the average values of the PWM signal. In this case, there is no waveform, therefore, the average value is 0. Here the on time is 25% of the total time. This is the total time, the on time is 25%, therefore, the average voltage is VCC by 4. Here it is 50%. So, the average voltage is 50%, VCC by 2. In this case, it is 3/4 of VCC, because the duty cycle is 75%, and if the output is continuously high, the duty cycle is 100%, and so you get full VCC out. Now, as I mentioned, we can generate a PWM signal using a software loop. All you have to do is write a program in which an output pin, any pin which can be converted, which can be programmed as an output pin of a microcontroller, can serve as a PWM output. What you do is you find out, you decide some amount of delay, and that delay you should be able to replicate. So, let us say that I am able to, let us say I have a total delay of T d. Let us say this is the delay function I can write, this is the amount of delay that I can generate in a guaranteed way. Now, what I will do is I will have, let us say 256 periods of this Td into Td. Now, in this period of 256 into Td, I can choose that the signal, the pin is high for certain period and is low for the rest. Now, if this is some integer multiple n into Td is equal to, is kept at logic 1, and therefore, 256 minus n into Td is the time for which the output is 0, and therefore, I will be able to generate a duty cycle which is equal to n upon 256 is equal to the duty cycle. Now, by changing this n, so I can increase n from this to 256. As the value of n increases, you will see that the duty cycle increases, and because this is being done as a software program, by writing an appropriate value of n, I will be able to change the duty cycle from any value of n equal to 0 to n is equal to 256, and therefore, I get a range of duty cycle which gives me a resolution, that is I am able to resolve the duty cycle of 1 part in 256. This is the variation. I can't, if I want to make output analog voltage smaller than this resolution, this particular arrangement will not be able to do it, but 1 by 256 is the resolution into VCC is the kind of minimum voltage that I can generate out of such a waveform. Let us see what kind of program we can write, so that we are able to generate this PWM signal. What we are going to do here is we are going to apply this software generated PWM signal onto the onboard LED of the lunchbox. Therefore, you do not have to make any additional connections. All you do is understand this code, download this code, rebuild it and download it into your lunchbox. When it starts working, you will see that the intensity of the LED increases from minimum to maximum. It goes up, then it falls like this, then it goes up again, and so on and so forth. This is how it will appear. Okay, let's go through this program. Now, here to clarify, I have mentioned that there is large delay. The reason for this large delay is so that when you see this PWM waveform being applied to the LED, you can perceive, you can easily see that the LED intensity is going gradually from minimum to maximum, and then it is decrementing from maximum to minimum in the same, at the same rate. If we want to see this waveform on the oscilloscope, we will make some changes to the code. by reducing the delay time period. So, let us see. The first part of the code is that we have defined, we have hash included the mandatory MSP 430 header file. We have defined our LED to be on bit P1.7. Then we have created this delay function, which is nothing but it goes through a certain amount of loop calling this subroutine where the variable is 50. This gives you certain amount of delay, we will see how much delay it gives you. And then this is the main part of the program, that is all you require. This entire code is able to generate software PWM in which it changes the duty cycle from 0 to maximum and then from maximum to minimum, and it repeats it. And so, the end result is when you download this code on the lunchbox, you will see that the LED on the lunchbox, the intensity of the LED goes from minimum to maximum gradually, and then in the same graduality it drops from maximum to minimum. So, what we have done is we have, as is mandatory when we are not using the watchdog timer, we have turned off the watchdog timer. We have set the LED which is connected, we have set the pin to which the LED is connected, that is P1.7. We have set the direction to be an output pin, and then we enter into a infinite loop here. We have infinite loop. What are we doing in this? We have a variable j which is going from 0 to 256, and for that period, for that loop, it turns the LED on. Here we are turning the LED on, then it goes to execute a delay subroutine equal to the value of j. So, if the value of j initially is 0, it is not going to execute that delay subroutine. On the other hand, if j is any non-zero value, it is going to call the subroutine delay with the variable j. That means, if j is 1, it is going to go back into this and it is going to loop through this once. If j was 2, it is going to loop through it twice, and so on. So, it is going to turn the LED on for a certain period of time from time t equal to 0 to multiples of this basic time period into the value of j. And so, what you will see is that the LED is on for certain amount of time, and for the rest of the time, that is 256 minus this count, is going to keep the LED off. We are turning the LED off here, and then we are delaying for how much time? 256 minus j, and we are going through this loop by changing the value of j from 0 to 255. So, what should you see? That you will see that the LED intensity goes from minimum to maximum. Then once this loop is over, it enters into the second loop. Here it decrements the value of j from 255 till it reaches 0. Now, the duty cycle you will see goes from maximum to 0, and then this loop repeats. Now, based on the delay cycle here, you would expect a certain amount of period. The period of your PWM signal will be 256 into the delay period, delay time period, delay function. This is the basic period of the PWM signal. Now, this is sufficient and suitable if you want to see the intensity of the LED, but if you want to observe it on the oscilloscope, this may be too slow, and therefore, what we have done is we have simply recompiled this code by changing the value of the delay cycle here from 50 to 1. It is still going to call this function x number, total number of 256 number of times for one period, of which certain amount goes for the time when the LED is on and the rest the LED is off, or in this case pin is high and for the rest 256 minus that amount the pin is low. So, what we do is we recompile this code. Now, you see the delay cycles we are invoking is just 1. This will lead to a certain amount of time period, and let me show you the PWM signal. You see the time period of the PWM signal from, if you see from here to here is, as you see here, it is 1 kilohertz. Now, in this 1 kilohertz waveform, what are we doing? That this 1 kilohertz waveform we are repeating, we are changing the value of duty cycle in every step from minimum to maximum in 256 steps, and then from 256 to 0. So, therefore, there are 512 steps in the overall variation of the duty cycle from minimum to maximum and from maximum to minimum. Therefore, what kind of waveform of the signal that you expect, the analog signal? It will be 1000 hertz approximately divided by 512, approximately you should get 2 hertz. Let us see whether you get a 2 hertz signal or not. Now, as I mentioned, to be able to get 2 hertz or whatever signal which is being used to modulate this duty cycle, the frequency of your PWM signal is here. This is 1 kilohertz, and your message or the information which is modulating this is somewhere here, and you want to extract this. So, what you do is you apply a low pass filter. You pass this PWM signal through a low pass filter, and the simplest low pass filter is a RC filter, which is like this. If I take R and C, this is R, then C. The product of RC, this frequency that comes out of here 1 by 2 pi RC is the 3 dB frequency equal to, here in this case for 1.5 and 10 microfarad you get 10 hertz, which means in my signal I have something like this. So, this 3 dB is 10 hertz here, but my carrier frequency, that is the PWM carrier frequency, is 1 kilohertz. As you see, it is much higher, and my signal, the signal which is modulating this is much lower. As I mentioned, we estimate this signal to be 2 hertz. It is very well within the pass band of the low pass filter. So, if I apply a low pass filter to the PWM signal, at this point I should be able to see the signal going from 0 to maximum, back to 0 and so on, and the period of that signal should be what we have predicted to be around 2 hertz. What we did was we took the output from P 1.7, applied a external R and C. As you see here, this is the resistor here, and this is the capacitor. This is 10 kilo ohm, 1.5 kilo ohm in fact, as you see here, 1.5 kilo ohm resistor and 10 microfarad electrolytic capacitor. The resultant was this frequency, and here is the filtered output, and as you see here the time period is indeed 2 hertz. That is, the time period from here to here, this is the time period, is 2 hertz, and this matches exactly what we have been saying. The requirement is that there should be large gap between the PWM carrier frequency, that is the frequency of the PWM signal, and the signal frequency which is your message, and once that is there, you can easily filter out the PWM carrier waveform by passing it through a low pass filter. If the difference is not large, then you will need a much sharper low pass filter, which means you will have to increase the order of this filter. Okay. We have already seen this, how the duty cycle goes from in this case 28%, 52% and 72%, but the period remains the same. Period remains the same. Why? The sum of on time and off time is constant. Now, this is a method which uses a program to generate a PWM signal. If we do that, then the microcontroller is unable to do anything else, and so this is very useful only when this is the only thing your microcontroller has to do. But if the microcontroller has to do multiple things while generating a PWM signal, then the only way you can achieve that is by outsourcing, by offloading the job of generating the PWM signal to a peripheral, and in this case a timer is often very useful for doing that. In fact, MSP 430 microcontroller timers have specialized features which allow it to generate PWM. All you have to do is specify the duty cycle that you would want the PWM signal to operate at, the frequency of the PWM signal and the resolution. You know, you can control all these three things using the hardware PWM feature of MSP430. Let me repeat, what can you do? You can specify duty cycle, you can specify the time period, that is the frequency of PWM, and 3 you can specify the resolution. Resolution meaning what is the minimum variation in the duty cycle that you can achieve in the entire period, which means if I have a 8-bit counter, my 8-bit counter has 256 possibilities. So, I can only change the duty cycle one count in 8 bits, one count in 256 counts. On the other hand, if I have a 16-bit time counter, 16-bit, then I can still vary 1 bit, I can change the duty cycle by 1 bit, but 1 bit out of how many? 1 bit in 65,536. So, MSP 430 allows you to go all the way from any arbitrarily small range to a large range of 16 bits. Now, here is a impact of choosing or varying the resolution of the PWM signal. If you choose a 8-bit, PWM signal, 8-bit PWM, what that does essentially is that here is my PWM generator. PWM generator requires a clock, the system clock or the clock that is being fed to this generator, in this case a timer. It will generate PWM. The frequency of PWM will be equal to f clock, that is the frequency of this clock signal, divided by 2 raised to power n, where you are chosen a n bit PWM. So, if n is 8, and let me take an example, let us say the clock is as we know the default clock when you run your timer, when you run your MSP 430, the default clock at which the CPU starts working and the same clock can be fed to the timer is 1.1 megahertz. Then what happens is you have 1100 kilohertz divided by 256 is the frequency of the FPWM will be this, and this will be roughly 4.3 kilohertz. Now, the PWM frequency needs to be very high. Why? So that it can keep, you can keep a distance between the signal frequency, the frequency of the signal of interest, the message frequency and the carrier frequency. The frequency of the PWM signal is what we call as the carrier frequency. You want to have a large gap between the two. Why? So that a reasonable filter can remove the carrier frequency, and so that you can extract the analog voltage. And therefore, it is very important that we should be able to have a high frequency of PWM signal, but the PWM frequency is largely determined by the system frequency, that is the frequency at which the timer is being clocked. And as you know, I can change the, I can dynamically change, or I can at reset I can decide to have an arbitrary value of the clock frequency. The default is 1.1 megahertz, but I can change that and I can use the DCO and use the DCO to generate M clock and SM clock, the two clocks which are used by the microcontroller, and I can go from 1.1 megahertz to 16 megahertz. So, if I choose to have a 16 megahertz clock, and now if I choose to have 8-bit PWM, what will I get? 16 megahertz divided by 256 will give you roughly 16 times more frequency than the 4 kilohertz that you got. You were getting about 4 kilohertz when the signal clock frequency was 1.1 megahertz. Now, it has become 16 times more. Therefore, this will lead to roughly 64 kilohertz PWM signal FPWM for 8 bits. Now, if I want higher resolution, let us say I want a 16 bit resolution, then what I can do is I can still choose to have the highest, because I can't go beyond 16 megahertz on the MSP 430, G2553 and G series of microcontrollers, but 16 megahertz divided by 65536, this will roughly give you, let me calculate here for you, it will give you roughly 240 hertz PWM carrier frequency. And so, in many cases this could be sufficient. If not, you can trade the resolution, you can choose to have a low resolution instead of 16, this is a 16 bit resolution, instead of 16 bit resolution you can go for a 12 bit resolution. 12 bit will give you 2 raised to power 12, which is 4096, and therefore, you will get roughly 16 times this frequency, about 3.5 kilohertz PWM frequency. So, you can, using the keeping the constraint of the clock frequency in mind, the system clock frequency in mind, and the resultant PWM frequency, you can choose to have a higher resolution or a lower resolution, but be aware that it is going to impact your carrier frequency of the PWM signal, and if for a given application the carrier frequency is sufficient and suitable, why not, you can choose to have a higher resolution. If not, you can give up the resolution, choose a lower resolution and have a higher frequency of PWM signal. So, let us see how the timer functions, timer modes allow us to generate the PWM signal. For that, please look at this block diagram of the timer. As we saw in a previous lecture on the timer operation, it consists of many parts. The most important part is the timer, which in this case is a 16 bit timer. MSP 430 timers are all 16 bit timers. The source of the clock for these timers can be through many of the input signals, input signal which is available from one of the pins, or a clock which is internally generated. As you see, you can choose the A clock, ACLK, or the SM clock to be the source for the timer, the counting purpose. Now, you also know that the timer has a control register through which you can choose the mode of the timer. There are 4 modes. One, you can stop the timer, you can make it go in the up mode, or you can go it in the up down mode, or you can make it go in the continuous mode. Now, based on that, the timer will go from 0 to the maximum value. If it is the continuous mode, the maximum value is the maximum value of a 16 bit number, which is FFFF. On the other hand, in the other 2 modes, that is the up mode and the up down mode, you have the maximum value that the timer will count up to will be determined by the control capture register R0. All right. So, it is going to go count up to that, and maybe it will come to 0 in the up mode, or from that value it will decrement to 0 1 bit at a time. That depends on the mode of the timer. Now, that timer value is available on the output bits of the timer, 16 bits. They can be compared to a register whose value is in timer compare register R2, or for that matter R1, or it could be captured into this, or it could be compared with a value which is stored in these registers. So, there are 3 channels. Channel 0 is special, but channel 1 and channel 2 can be used to capture the value of the timer, or the captured value could be compared with a value stored in those registers. And using that, in the last exercise when we looked at the timer, what we saw that using this we were able to generate interrupts. So, that we knew from the time that we started the timer, we wanted an interrupt after a certain period of time, and once that interrupt was generated, we restarted the timer and so on. Now, in this case what we are going to do is that we can actually do more actions on the compare functions. Once the value is compared, you can decide what you want to do, and we want to send the compared output to output pins, and this is the way that we will be able to generate a PWM signal. Let us see how that works. So, the timer A output unit has a capture compare block which contains an output unit. Here is the output unit, this part, this is the output unit of the timer. The compare mode is selected when in the timer control register you set the value of CAP equal to 0. If CAP is 1, then it goes in the capture mode. We are going to consider the capture mode in a subsequent lecture. When the timer value is equal to value in the TCCRRX, which is one of the internal signals, the EQUX, meaning if this is TACCR1, then you are going to talk about EQU1 will be set, which affects the output according to the output mode. Similarly, the output unit is used to generate output signals such as PWM using another mode. Each output unit has 8 operating modes that generate signals based on the EQU0 and EQUX signals. EQX here is either 1 or 2. The output modes are defined in the out mode bits in the timer control register. Let us see what are those output modes. Before that, as I mentioned, the timer itself can be operated in 4 modes, and this is programmed in the timer control register. You can stop the timer, you can make it function in the up mode. In the up mode, the timer counts from 0 to a value stored in TACCR0. So, TACCR0 is a very special register. Therefore, that cannot be used in PWM signal generation. R1 and R2, in some cases R2 can also be used. TACCR0 is used to store the value with which the timer value will be compared. In the continuous mode, it will go from 0 to a maximum value that a 16-bit allows, and in the up down mode it will go from 0 to the value stored to this, and then from here it will decrement to 0. And so, in the up mode the waveform is more like this, in the up down mode it is like this. So, you get a sawtooth waveform of comparison in the up mode, and in the up down mode you get a triangle waveform. Here are the output modes. If the out mode bits are 0 0 0, this is called the output mode, and the out signal will be immediately available on that pin. You can have the set mode, you can have toggle reset, but the one that we are interested in is the combination which is 1 1 1, in which the bit is reset to 0 and then is set to 0. When is it reset? The output is reset when the timer counts to the value stored in this, and this is for example TACCR1, and it is set when the timer counts to value stored in TACCR0. So, using TACCR1 and TACCR0, using this mode which is the reset set mode, you will be able to generate a PWM signal. So, let us look at that, what happens. So, you have chosen the up mode in which the value is going to go from 0 to the value stored in TACCR0. When it matches the value of TACCR1, here this is the 7th mode, the output toggles, and then when it reaches this value it is set. So, it is going to remain high for the time, for the count stored in TACCR1, and for the rest of the time it is going to become 0. Therefore, by changing the value of the count stored in TACCR1 of any number from 0 to TACCR0, you are able to change the duty cycle from 0 to 100%. The TACCR0 itself can be modified, and if you modify it, it will change the period, overall period of the PWM signal, and that is what one means when you say that you are able to change the resolution. So, if I choose TACCR0 value to be the maximum value, that is 65536, the resultant resolution will be 16 bits. On the other hand, if I set TACCR 0 to 256, that means the resolution of the PWM signal will be 8 bits. We are going to use this mode, we are going to load values in the TACCR 0 and TACCR 1 register appropriately to generate similar waveforms that we generated in the software PWM mode. Now, if you want to use the timer for PWM, the output signal can be routed on any given pin. In this case, we will route the pin on this P1.6, that is TA 0.1, and let us see how we do that. These are the pins which are associated with the timer A0, input and output pins. We are interested in this. We are going to use CCR1. Here we are going to store the value which will determine the frequency of the PWM signal, and this will give us output on P1.6. You can also route it to P2.6 or you can route it to P1.2. You can do that. If on the other hand you are using timer 1 for PWM, then you have the timer CCR1 available on P2.1 or P2.2. Here it is P1.6, which is pin number 14, and these are for 20 pin ICs, which is the ones we are using on our lunchbox. Now, to be able to tell the microcontroller, because you see you are going to use P1.6, which is otherwise a input or output pin, it is port 1 bit 6, you want to use it for timer function, that is PWM function. So, you must tell the control registers associated with the port 1 that you want to use this pin as a PWM signal, and for that what we are going to do is, for this pin we are going to invoke this function. So, in the P1 dir register it is 1, so that it is an output. P1 select we will write 1, P1 select 2 we will write 0, and for the rest of them we will write 0, and so you must program the ports associated with P1 point port 1 in this fashion, so that P1.6 can act as a PWM output signal associated with timer 0. These are the registers associated with timer A. We have already seen that in the previous lecture. So, I am not going to repeat that. You will see it when we look at the code. Now, to use the PWM signal using a timer, you have to do various steps. You have to configure the timer in up mode. The timer value goes from 0 to the value stored here and it repeats. In up mode, the up mode is selected by ORing this is a mask to the timer control register. Another step, the value of this is filled and this will determine the frequency or the period of the PWM signal, and then you write a value in the CCR1 which will decide the on time, that is the duty cycle of the PWM signal. And last but not the least, you must tell the port that you want to route the output signal, you want to select the output mode 7 and you want to route it into the P1.6 pin. Now, here is an example what will happen, that when the counting starts, the output will become high and it will remain high till the counter value reaches TACCR1. Then it turns low and it remains low till it reaches the value of TACCR 0, and then this cycle repeats. Now, as you can see, if I increase the TACCR 0 value, it is going to increase the period, but it will give me higher resolution. If I reduce it, it will reduce the period, meaning it will increase the frequency, but it will also reduce the resolution. In our lunchbox, we do not have any LED on the PWM on P1.6. As you know, we have a LED on P 1.7, but unfortunately we cannot route the PWM output on P 1.7. So, we have to connect an external LED with a series resistor to P 1.6. Here is the code. We have decided we have connected a LED to P 1.6. These are the registers. This is a subroutine which we are going to call for timer 0. We are selecting the LED as output, and we are selecting the timer output on this, and then we are setting a value in CCR 0 equal to 255, which means we are choosing a 8-bit resolution. We are choosing mode 7, output mode is mode 7. The value in the CCR1 register is initially set to 0, which means initially the duty cycle will be 0, and an interrupt is enabled, so that after every compare, after every one period of the PWM signal, you will have an opportunity to either change the value of CCR1 or CCR0 if you like. So, we have enabled the interrupts, and we are using the timer clock, getting the timer clock from SM clock, and the mode is in the up mode. Here is the main program. We have simply turned the watchdog timer off. We have called that function which we just discussed, and we have enabled the interrupts, and we are just waiting in a infinite loop. Now, every time the timer overflows, that is when it reaches the TCCR 0, it will generate an interrupt and it will go into this, where what we are doing is we are simply incrementing the value of CCR 1. And so, CCR 1, as we saw, CCR 1 started with 0, it will keep on incrementing because of this, but the moment it reaches 256, we want to make it 0. So, if after incrementing the value is 256, make the value of CCR 1 equal to 0, which means the value of CCR 1 will go from 0 to 255, and when it is 0, the duty cycle will be 0, when it is 255, the duty cycle will be 100%. And once you run this program, you will see that the intensity of the LED goes from minimum to maximum, abruptly going to 0, so that the intensity will give you a sawtooth waveform because of this. Here is the filtered output. Since we know that we are the DCO frequency is 1.1 megahertz and we are choosing a 8-bit resolution, the resultant frequency will be about here is the PWM signal, it will be about 4.3 megahertz, which 4.3 kilohertz, which we just calculated. And because there are 256 levels, so 4.3 kilohertz divided by 256 will give you the resultant signal, which as you see here is 16 hertz, 17 hertz, and this value has been obtained, this signal has been obtained by filtering the PWM signal. This is not being generated by the microcontroller by itself, this is the result of a filtered output, and the filter characteristics is that it has a frequency of cutoff frequency of 154 hertz because of these values involved, and this is much lower than the PWM signal frequency. Therefore, the PWM signal will be filtered out, and it is much higher than the message, that is this signal frequency. Therefore, that sawtooth waveform will flow easily out of it, and that is what you see here. Here is another program in which certain things are done. One, the DCO frequency has been jacked up from 1.1 megahertz to 16 megahertz. Rest everything is changed, apart from instead of 8-bit PWM we have chosen 16-bit PWM. I strongly recommend you go through this program and see the output. Now, you see, because the 16 megahertz frequency was used, divided by 65,536 will give you a PWM, basic PWM frequency of just 236 hertz, and this if you further divide by if you are going to change the duty cycle all the way from 1 to 65,536 will give you a frequency which is 236 hertz divided by 65,536 will give you a very small frequency, and that what you can see here. The frequency is 3.56 millihertz, and this has been obtained by putting a RC filter, low pass filter of just 3.28 hertz. So, I strongly recommend that you go through this program and understand how a high resolution PWM based on the hardware feature has been generated using this microcontroller. I thank you for listening to this. I hope it opens your mind as to how digital signal of the type called PWM can be used to generate analog waveforms. You can use the same feature and generate arbitrary waveforms. You can create sine waves, you can create cosine waves, you can create sine and cosine together, something like this. Suppose I want a sine wave here and I want a cosine wave, say something like this. So, this is 0 and this goes, let me draw it again. So, let us say this is your sine wave and you wanted another waveform which is synchronized with this, but something like this. So, you can easily create two waveforms which are matched, locked to each other under the control of the microcontroller. You can easily do that using a PWM function. I am going to put up some exercises for you, so that you are able to generate such waveforms using the PWM function. Thank you very much.